good morning to all of you. Welcome to another session. In this session, we'll be discussing particle accelerators. So I think we are almost at the end of the course. Maybe after particle accelerators, we'll be discussing particle detectors. And I hope with that, our particle physics will be complete. After that, we'll go for the most important topics, remaining most important topics. So before I proceed further, let me know if everything is all right. And guys, our new batch in the English language has been launched, so you can join if you are interested. Let me know if everything is all right so that we can start. Let me know if everything is all right so that we can start. Okay. I hope everything is all right. So let's start. Particle accelerators. So as per the name suggests, particle accelerators are used to accelerate particles, charged particles. Now, what are the accelerators we have? In India, there are few places where we have accelerators. In New Delhi, we have IUAC, Inter-University Accelerator Center. So there we have accelerators. In Kolkata, in VECC, Variable Energy Cyclotron Center, we have accelerators. And maybe in TIFR, we have accelerators. So in few places only, we have accelerators. So what are these particle accelerators? These are the devices that use electromagnetic fields to accelerate charged particles such as electrons, protons or ions to a high speed. This is the purpose of using accelerators, often near the speed of light. So it often goes to the relativistic regime. These particles are then detected along specific paths for experiments in physics and engineering and for medical applications. Particle accelerators are a very important tool to understand the structure of matter, energy and the force that govern the universe. Mainly two types of particle accelerators we will be talking about today. One is this linear accelerators called a linac. So here the particles are accelerated in a straight line using a sequence of electromagnetic fields. The polarity are changed sequentially and the particle gets accelerated from one stage to other in a straight line. So that is why the name linear accelerators. And the second type of accelerators are called circular accelerators. In circular accelerators, we use magnetic field, perpendicular magnetic field to accelerate or in fact to guide the particles in circular paths. So these are the basic difference between linear accelerators and circular accelerators. So we'll discuss them one by one. Good morning, Harry. Okay. So let's start with this linear accelerators, or in short linac. This structure is very easy, you will understand easily. So look at this, what we have in linear accelerators. It is a type of particle accelerator where charged particles like electron or proton are accelerated in a straight line using a series of alternating electric fields. Alternating electric fields, you can see this structure. So here you have the source from where the particle is generated, and this particle is subjected to this cylindrical structure like this. So we can give negative or positive, we can see negative or positive potential on these cylindrical tubes, and see their lengths are not equal, their lengths are constantly increasing. As you can see, we'll find out the mathematical expressions for these lengths. The lengths are increasing, and you see these tubes, cylindrical tubes, are connected to an RF oscillator. So you can see an alternating oscillator, alternating electric fields are given to this, and as you can see, one end of the accelerator, one end of this alternating field is connected to the cylinders like this alternately. let's say it is connected to C1, this one, this end is connected to C1, then C2 is missing, then C3, and obviously if there are more number of such tubes, then after C1, C3 we have C5, and then you see C2, C3, C2, C4, C6 in this way. So that you see this was an animation, but because this is a PDF, we am not able to show. But this plus minus keeps on changing. Okay, the particle, let's say it will see minus here, then again it will see plus here. This will be minus again, then plus and minus. In this way, it will keep on changing. So alternating electric field, and in this way, this particle gets up this exact potential to get accelerated. Okay, so this is the basic structure of the linear accelerator. Do you understand this? This is the given potential. You can see here it is negative, here it is positive, here it is positive, here it is negative, and if the polarity becomes changed, okay, in next moment this will be positive, so we will have positive here. Okay, then it will become negative. I try to draw in this way. It will become negative, then this becomes positive. Okay, then this become negative. Negative means lower voltage, then again positive, and so on. So this keeps on changing, alternating electric fields. Yeah. Now this structure is important. We have this ion source. Ions are generated from it, and it is passed through a series of such tubes, drift tubes. Negative, positive, negative, positive. So alternatingly, this polarity will keep on changing. And the length is also increasing. Okay. This shows the movement of the charged particles. Two pictures have been shown, because you see here negative is shown, in the next moment it will become positive. Here it was positive, next moment it will become negative. Here it was negative, it will become positive. Just a moment. Now, what is the basic principle of linac? Linear accelerator increases the velocity of the charged particle in a series of steps along a straight line. Particles are exposed to an accelerating field repeatedly. Energized by linear pulse at radio frequencies, this timing ensures that the particle receives an extra push at the correct moment in phase. Okay. So now you can see, if Ln is the length of the nth cylinder, now we are taking any of the cylinders. Let's say this cylinder. Okay. So nth cylinder we are taking. Lth cylinder will have a length, let's say Ln, and if the speeds inside the cylinder of the particles is Vn, then the time taken to cross this cylinder will be Ln by Vn. Vn is the velocity of the ion inside the nth cylinder. Now, what is the condition for synchronization? Look, the particle is coming or going in this way, it sees a tube, whether it is positive or negative, then the length of the tube is increasing. So constantly it is, you need to change the polarity to plus or minus. In this way it is going. Now as you are changing the polarity of the tubes, like at what time interval you have to change this polarity so that this particle gets accelerated. Okay na? So that thing you need to know. So this changing polarity frequency should be T by 2. Particles from the ion source itself have an energy through the lens. Now from the ion source, let's say, and look, this is a negative, okay. Initially the particle or ion from the ion source are bombarded through the first tube. So once it reaches to the first tube, it will get attracted because of this polarity, okay, and the polarity will be kept in such a way that this particle get accelerated. It is like if you have an electron, if you have a proton, let's say, if you keep a negative potential, proton is positive and this is negative, so it will get attracted. So in this way you get the acceleration. Now by changing the polarity, you maintain this proper acceleration. It will not get accelerated if you only keep negative. It will not get accelerated properly. It will remain constant. It will achieve constant speed. But by changing this potential, it gets accelerated. So it gets the appropriate potential to get speed up. Yes. So here let's say the particle will have some velocity. Now here it was positive, so it will become negative, so particle will get accelerated more. So here the velocity will be more, and after crossing this gap the velocity will be more. In this way it will get accelerated. Velocity must increase, otherwise where is the acceleration? And this condition of the synchronization condition requires that Tn must be equals to T by 2. The time interval in which you need to change the polarity is T by 2. So that is 1 by 2f. T is equals to 1 by f. F is equals to T by lambda. So it is lambda by 2c. So this formula is very important. Tn is equals to T by 2 is equals to 1 by 2f lambda by 2c. T is the time period, f is the frequency of the RF oscillator. Now why there is a T by 2 factor? T by 2 factor is there. The reason is that the electric field in linac oscillates sinusoidally. The potential you have given, it is sinusoidal. So if it is sinusoidal, once it will reach positive, another time it will reach negative. This is positive, this is negative, positive, positive, negative. In this way it will go on for completing one's full cycle in time t. For particles to constantly receive an accelerating push at each gap, this is the gap between the two accelerations. It is talking about this region and the particle is here. So you need to maintain appropriate potential at these tubes plus or minus. To constantly receive an accelerating push at each gap, they need to encounter the field at every half cycle from one peak to the next, which corresponds to the half period. To ensure that the particle is always in the accelerating phase of the electric field as it moves through each gap, maintaining the synchronization required for continuous acceleration. So the synchronization condition is the frequency of the RF oscillator should be in the form of T/2, you know, like it should be 1/2f actually. Is it clear? So it is like, look, inside the tube it will maintain the constant speed. As it leaves the tube, in this gap it will get accelerated. You know, in the gap it get accelerated. Inside the tube the velocity speed remains constant. Inside the tube speed remains constant, because that is the constant potential thing. If you consider a particular tube, it is constant potential, so it will the particle will move with constant speed. Now as you come to the gap, it will get accelerated. Okay, and who is accelerating? This tube is accelerating. Now inside this tube it will continue to go at constant speed. Now as it leaves this tube, it comes to this gap, it will get accelerated by this tube. Okay, by this tube. In this way, the particle will always remain in the accelerating phase of the electric field. Now let's say you have a charge, let's say Q. So we are basically trying to find out the drift tube length. These tubes are called drift tube. Okay, drift tube length and the energy of the ions. Let's say we have an ion of charge Q be accelerated through the nth drift tube. Nth drift tube. So it is like we have this nth drift tube. So its length will be ln. The length of this tube is, let's say, ln, and here the particle will move with speed vn. After this you have ln plus 1, or before this you have ln minus 1. Let an ion of charge Q be accelerated through the nth drift tube at a time when the RF oscillator, the radio frequency oscillator, provides maximum potential. Maximum potential Vm across the gap. So RF potential, you know, it is varying like sinusoidally in this. So we are considering that it is accelerated through the net tube when it is at the maximum, it is providing the maximum potential. Let's say this maximum potential is Vm. So what will be the energy imparted to the ion? Energy imparted to the ion. You know the formula. Look, Q times Vm. This would have been the energy imparted to the ion. But you see, before reaching to the nth tube, it has undergone n accelerations. You see, here one acceleration it has undergone, here second acceleration it has undergone, here it has undergone the acceleration for third time, fourth time, fifth time, in this way nth time. So the total energy of the ion will be n times q into Vm. Understood? Since the ion has undergone n accelerations, in the preceding n gaps, and each acceleration gives rise to an increment in energy value of q times Vm. Can you write it? So if this is the current speed of the particle, what is the kinetic energy? It is half m Vn square. This is the kinetic energy of the particle. So this must be equals to nqvm, right? So from this we can get the velocity of the particle inside the nth tube. This is your nth tube. So what is Vn? Vn is equals to root over 2nqvm divided by m. Okay, now we know what is ln. Ln is equals to Tn Vn, or Tn is equals to ln by Vn. We know this relationship, we can use that. And furthermore, we know also this Tn is equals to 1 by 2f, and Tn is equals to ln by Vn. So ln by Vn is equals to 1 by 2f. So ln is equals to Vn by 2f, right? Ln is equals to how much? Tn into Vn. Tn into Vn. Now Tn is 1 by 2f, so this becomes Vn by 2f. So this is 1 by 2f times Vn. Vn is this root over 2nq Vm by m. So if I take this 2 inside, so it will become 2. 2 inside root, it will become 4. So 1 upon f root over nqvm, 2 by 4 is 2, so it becomes 2m. So what do you see from here? You see the length of the nth tube is proportional to root over n, isn't it? Thus we can say the length of the drift tube is proportional to root over n, because q is fixed, Vm is also fixed, mass of the ion is fixed, frequency of the oscillator, that is also fixed. So we can say that the length of the drift tube, nth drift tube, is proportional to square root of n. So you see how the length will keep on changing. If you consider this one, this is the first tube, so this will be root over 1, it will be root over 2, it will be root over 3 unit, it is root over 4 meter, and whatever unit you used. Okay, so they will be in this ratio. Root over 1 is to root over 2 is to root over 3 is to root over 4. So as you can see, it is keep on increasing. So from this we can have this conclusion that therefore the length of the drip tube should be proportional to. So look, this condition we have derived keeping in mind that the polarity should be changed in the interval of t by 2. So we have used this condition of synchronization. After implementing the condition of synchronization, we have got this. So if you want to accelerate the particle should be there in the accelerating phase of the electric field, and for that you need to keep the length in this way, in the ratio of the natural number, square root of the natural numbers. So if you keep that those tubes in those length only, then only it will get accelerated, otherwise it will stop being accelerated. Understood? So the structure is important, very important, otherwise the particle will be fail to accelerate. Therefore the length of the drip tube should be proportional to the square of square root of the natural numbers, square root of the natural number. That is in the ratio of square root of 1 is 1, 1 is 2, root 2 is 2, root 3 to root 4, etc. So this expression of the kinetic energy we have used, this is non-relativist. If we have considered that there is no relativistic effect on the speed of the particle, as you keep on increasing the speed of the particle, it may go to the relativistic regime. So this is the calculation made for non-relativistic case. Now if the particle become relativistic, then this synchronization will not be there, and as a result the particle will not get accelerated. So you see, if you take the, let's say, electron, so electron will acquire high speed very easily, so that will reach to the relativistic regime. And if you keep the arrangement same, like you in the ratio of the natural number square root, then it will not work for the electron, right? So that is why we say if we treat the things relativistically, if treated relativistically, what we will have? If treated relativistically, and E be the total energy of the ion, then what you will have? Then you see, this is the total increase in energy N Q V M, this will remain as it is. Now what is the kinetic energy? Total energy minus rest mass energy m naught c square. This is the total energy, this is the rest mass energy. Okay. Now what is the total energy? E is equals to gamma m naught c square. This is the total energy, you know. So this is m naught c square divided by root over 1 minus v square by c square. So you have to use this equation if you treat relativistically. Now for the particle like electrons, yes, mass variation will occur, there will be mass increase, a relativistic mass increase. You know, m is equals to m naught time gamma. So if the mass increase, so this acceleration will not be possible. So this is also this is the limitation of linac actually. So where you will use this? We cannot use light particles to accelerate inside the linac. If you use light particle, what will happen? It will reach to the relativistic region. So what are the usefulness? Usefulness of linac. The linear accelerators are useful for accelerating protons. The proton is a little heavier than electron. Little means very much heavier than electron as compared to the mass of electron. For accelerating protons and other heavier ions. So you see, we are not accelerating the lighter ions. For that we will use other accelerators, maybe cyclotron or betatron. Okay, linear accelerator is useful for accelerating protons and other heavier ions to energize energies of about 32 MeV. Is it clear, guys? What happens to my throat? The next accelerator which we will be talking about is cyclotron. Is this linac is clear to everyone? Simple linac. Linac is nothing. There is nothing complicated in linac. Simple. Let's move on to cyclotron. So in cyclotron, the particles are accelerated in the form of circle. Okay, here also we use accelerating potentials, okay, RF oscillators, but here you see these two things are looking like a D. How D looks like? You see, D looks like this, right? So here, as you can see, this is one D. This is also another D. So these are called Ds. D-E-E-S, Ds. So the particle is kept here. Okay. Now the particle gets accelerated. So inside the D, there will be constant speed, and as it moves through these gaps, it is accelerated by using this potential of the D's. The particle is accelerated, and you can see it will get accelerated in this way. It will increase constantly its radius in this way, maintaining proper synchronization, and as it reaches to higher radius, its speeds will get increased, and when it is accelerated to appropriate value, it will be removed in this way. You see, so a perpendicular magnetic field has been applied. You know, whenever a charged particle enters into a perpendicular magnetic field, it makes a circular trajectory. You know it already. So this thing is used. You see, the magnetic field has been applied in a perpendicular direction. Your particle is here, and it gets accelerated in. So cyclotron was one of the earliest type of particle accelerators. It is still used as the first stage of some large multi-stage particle accelerators, and it makes use of the magnetic force on a moving charge to bend moving charges into a semicircular path between acceleration by an applied electric field. Okay, so this property has been used. Electric field is applied between the D's. This is one D, this is another D. Magnetic field is applied perpendicular to it to make the path of this charged particle circular. The applied electric field accelerates the electrons between the D's. Between the D's means it is talking about this region. This is talking about this region. And inside, between the two D's, this gap. The field is reversed at the cyclotron frequency to accelerate the electrons back to the gap. So in linac, what was the acceleration time? So it was like t by 2. Okay, so corresponding frequency is 1 by 2f. Here the field is reversed at the cyclotron frequency to accelerate the electrons back across the gap. So it is 1 by f. Understood? So I have a very good picture of it, another picture which will help you understand the whole thing very clearly. So here these are the two D's, this is one D and this is the other D. Particle is kept at the center, and as we apply, magnetic field has been applied in the perpendicular direction, and electric field, if you maintain this is this positive and this is negative. So obviously in between positive and negative potential we will have some electric field, right? If you have a positive plate and negative plate, in between them there will be created electric field, and you have ion means charge. If you keep a charge in the electric field, it will get accelerated, right? If you keep a charge in the electric field, it will get accelerated. It will feel a force QE. Okay, this is the force. If you equate it mass time acceleration from this, you can get the acceleration QE by m, right? Because of this existence of electric field, you will get acceleration. The particle will get accelerated here. So you see, particle start from here, comes to this point, it gets accelerated, and inside the D there will be constant speed, and as it leaves the D, its speed, it will feel a push. Okay, and it will reach to a higher radius. You can see it will reach to a higher radius. Same thing goes up, and it reaches to higher and higher radius, and its speed is increasing in this way, and finally when it is speed up to appropriate value, it is taken away. Okay, in this way this cyclotron works. Now where RF oscillator has been used, RF oscillator is used between the two Ds. Here electric field accelerates charge at the each gap at each gap crossing. So you see, RF oscillator gives a push, gives a high frequency alternating potential. Actually push it will give later, gives a high frequency. You know how high it is? High frequency is about 10 megahertz. High frequency alternating potential. Between the D's. To accelerate the particle. The D's act as electrodes. Now if you look at it from the side, what kind of picture you will get? This is from the this is the top view, right? Now if you look at from the side, what kind of look you will get? These are the vacuum within which these D's are kept. These are the magnetic poles. This is kept in vacuum, in a vacuum tank. This is the D, and this is the chamber C. Is there polarity change when the particle every time cross the disk? Yes, it is changing. Like you see, 10 megahertz means you can see the rate. It is changing in the at the rate of 10 into 10 to the power 6 times per second. High frequency oscillator alternating potential. So it is altering the potential at the rate of 10 megahertz. What is the meaning of this 10 megahertz? 10 into 10 to the power 6 hertz means you see 10 to the power 7 times per second it is changing this potential. Okay, you don't think the particle is going very low speed. It is not like that. It is moving so fast that you need to change the potential plus to minus, minus to plus 10 to the power 7 times per second. Otherwise, how will it get accelerated to the velocity of the speed of light? Okay, towards the speed of light, not exactly to the speed of light. It is going to relativistic regime. So you can imagine how fast this particle goes, and for that how fast the potential should be switched between positive and negative. Got it, Murli? Let's talk about the principle of action. We're basically going to talk about mathematically also. So let's talk about principle of action. Let a positive ion of charge Q leaves the ion source. The ion source is kept at this center. So from this, the ion leaves and enters into the D. Inside the D, what will happen? It is given a perpendicular magnetic field B, and it has a charge Q. And it will acquire velocity V. So it will experience low range force, right, inside the D. Ion source between the D's and enter the magnetic field. Let's talk about whenever it is maintaining negative potential, it is called negative D. When it is maintaining positive potential, it is called positive D. So let's say this is positive and this is negative for the timing at one instant. So after leaving this ion source, the charge is entering into this negative D. The point positive ion of charge Q leaves the ion source between the D's and enter the negative D. Enter the negative D at the instant with, let's say, velocity v naught, name it v naught, and it is obviously normal to the magnetic field, normal to the magnetic field, all magnetic lines of force, you can say. So due to the magnetic field B, it will experience Lorentz force. Due to the magnetic field B, the force F acting on the particle is given by particle. What are you asking? Polarity changes in the electric field region in the D's. Yes. Look, the electric field is existed at this region. At this region, right? In this region, the electric field exists. Now, if this is maintained at a positive potential, this is maintained at negative potential, the electric field lines will be like this. Okay, now let me just show you one example. Let's say we have this ion and it is going in this way. Okay, we have the D structure in this way. So these D's are given the potential. Let's say this is positive, this is negative. So what will be the electric field direction from positive to negative? And if it is a positive particle, it will get accelerated towards the positive plate to negative plate in the direction of the electric field. Now, as you can see from here also, the electric field direction is this. If you don't change the potential, what will happen? The particle will go, and here it is going against the electric field. So it will get deaccelerated, right? So if you don't change the potential at the exact time when the particle is reaching here, it will stop eventually. But if you, let's say, change the potential plus and minus, what will happen? The electric field direction will be this. So it is getting appropriate potential to get accelerated. If instead of this electric field in this direction, if this particle gets electric field in this direction, it will get accelerated. Okay, again when it is coming, if it is negative, it is positive, electric field will be this and its motion is this, so it will get hindered. So you need to change the potential again to positive, negative, so that electric field becomes in this direction and it accelerates the particle. So that is why the switching between positive and negative is important. Is it clear now? If you have a positive and negative potential, the electric field acts in this way. Yeah. I hope this is clear. So what is the force? Force is equals to Q into V cross B. This is the Lorentz force, right? Now V and B, you see the particle is moving along this direction and the magnetic field is outward, no, perpendicular direction. It has been, the magnetic field is applied perpendicular out of the page. So what is the angle between the speed of the particle and the magnetic field? Is 90 degrees. So V cross B will be V naught B sine 90, so 1. So Q times V naught times B. So you know, whenever a magnetic field acts perpendicular direction to a charged particle, it bends the particle's trajectory into a circle. Okay, so that is why we get the circular trajectory under the action of this Lorentz force the path of the particle is bent into the form of a circle, into the form of a circle of radius r0 given by, if a particle of mass m moves in a circular trajectory in the magnetic field, so this is half m v square is equals to bqv, okay na? Or you can say b q v naught means this expression, Lorentz force should be equals to the centrifugal force m v naught square divided by r naught. So from this you can get the expression of r naught is equals to m v naught by b. You must have heard about this expression before also. So this is the radius you get for the circular trajectory, and as this velocity v naught is constantly increasing, r is not constant. If v naught is increasing, r naught will also increase. That is why it is constantly increasing its radius. As you can see, the radius is this, and that is as it goes on, the radius keeps on increasing, right? Radius keeps on increasing in this way. Here r naught is not fixed. So for a particular value of speed, r naught is fixed. Now, when the particle is inside the d, the speed of the particle will remain constant. Its speed remains constant. Now, as it leaves the d, as it leaves the d's, and enters into the gap, it gets accelerated. The RF oscillator change the potentials on the d's synchronously. Now each time it crosses the gap, it is accelerated and give rise to this radius r is equals to mv by bq. You can write a general expression r is equals to mv upon b. Now what is the frequency of revolution? If I write the frequency of revolution formula, what is the frequency of revolution? Frequency of revolution of the particle in the circular orbit. So what is the formula for frequency? F is equals to V upon 2 pi r. This is the formula for frequency. Now we know the formula of R is equals to V by 2 pi into 1 by R. 1 by R is equals to how much? BQ by MB. So this is equals to BQ by 2 pi M. BQ by 2 pi M. So you can see F is independent of the speed of the ion. There is no expression of V here, so BQ by 2 pi M, and so it is independent of the speed of the ion and the radius of the path in the Ds. Radius of the path in the Ds. Look, this is the frequency with which the particle is moving in the circular radius. Now if this frequency exactly matches with the RF oscillator frequency, okay na? If it matches with the RF oscillator frequency, what will happen? Resonance condition will be established. If this moving frequency of this particle matches with the frequency of the RF oscillator, we will get the resonance condition. So obviously this is a fixed frequency oscillator. Here the frequency is fixed. Here we have considered the 10 megahertz. That frequency is 10 megahertz. So you can give the heading basic resonance condition. Basic resonance condition equation. Basic resonance equation for a fixed frequency cyclotron. Fixed frequency cyclotron. So if the electric field reverses its direction, means it is a RF frequency, okay na? If the electric field reverses its direction regularly at a frequency f prime, exactly equal to f, the field in the gap is always in the right direction. Right means not that right opposite of left, that is not that. Right means the proper, as I explained here. In this case, as I explained here, right direction means it should be when it is coming here, it should be along this to this. When it is coming here, it should be the electric field direction should be along this to this. It is talking about that right direction. It is always in the right direction to accelerate a charged particle by an impulse each time the gap is crossed. So hence, what is the resonance condition? So therefore, the condition is F should be equals to, or F prime should be equals to F, that should be equals to BQ by 2 pi m, which I have got here, BQ by 2 pi m. Okay. Just a moment, what happened to my keyboard? What happened to my mouse? Now it is. Now, what will be the energy of the particle? After getting accelerated, we have to calculate the energy of the particle, right? Energy of the particle. Let's calculate the energy of the particle. You know, the kinetic energy of the particle is Wk is half mv square. If I consider it non-relativistically, let's say Wk will be half mv square. The maximum kinetic energy, of the particle when it leaves the d, or when it leaves the cyclotron, means what we are talking about, we are talking about this speed when it is leaving the cyclotron. At this position, what is the speed? When it leaves the cyclotron is, let's say, Wm, kinetic energy maximum, this will be half m v maximum square. So half m, what is v maximum? We know, we can get it from the maximum radius. R is equals to mv by bq. So Rm is equals to mvm by bq. Okay. So Vm is equals to Rm bq by m square. This is because Rm is equals to mvm by bq. So Vm is equals to Rm bq by m. So this is equals to how much? Q square b square by 2m times Rm square. This Rm can be easily calculated now. Rm is the maximum trajectory. So if you are using a cyclotron, you will already know the dimension of the cyclotron. From that you can get the maximum radius, the maximum radius of the trajectory. Now what will be the maximum energy equivalent to this? maximum energy of the particle equivalent to the voltage given by. You know why we are calculating the voltage? We have accelerated the particle in this circular trajectory and we get a kinetic energy. Now if you say you maintain a potential, let's say V, and if you accelerate a charge q, what is the amount of energy you gain? It is q times V, right? This is the energy you get. So we need to calculate what effective potential we need to impart to gain this much of energy. So if we just equate qv to this maximum energy, kinetic energy Wm, we will get the equivalent potential, right? Wm by q. So what will be this value? 1 q is cancelled, so q b square by 2m times rm square. So this much of voltage you need to maintain if you want to accelerate the particles to this much of energy. Okay, so this is the equivalent voltage. Now can you tell me, after n number of revolution, what will be the kinetic energy? So it is moving in this circular trajectory. Let's say after n revolution, what will be the kinetic energy? In one revolution, you can see it is getting accelerated here, and another time it is accelerated here. In one revolution it is accelerated 2 times, right? And each time, what is the voltage maintained at the D? The maximum voltage Vm, or let's say V. Here another thing you just noted down, note, if the number of revolutions is n, then you see each time it crosses the gap, it is gaining energy qv, right? So one time in one revolution it is crossing the gap 2 times, so 2 times qv, and if it has completed, let's say n number of revolutions, okay, so it should be multiplied with n, and that will be the kinetic energy of the particle after n revolution, you can say. So this is the kinetic energy after n revolution. V is the potential difference between the this Wk is the kinetic energy of the charged particle after n revolutions. Understood? Now can you tell me what may be the possible limitations in this device? What may be the possible limitations in this cyclotron? So first of all, let's talk about its usefulness. What is its use? The cyclotron can accelerate protons, deuterons, alpha particles to an energy of 10 to 50 MeV. So here you can see we have not included electron, we have used protons, deuterons, alpha particles, heavy particles. So that all says the limitation of this. What should be the limitation? Can you tell me? The way the songs are being played, I fear no copyright claims comes into my video. A nice song, but the copyright claims would not come. What should be the limitation? Can you tell me? So in one word you can write what is the limitation? Relativistic mass increase. Okay, now this is the limitation. There may be relativistic mass increase of the accelerating particles. This is the serious limitations. So if relativistic mass increase happens, there will not be synchronization. M will be given by m naught by root over 1 minus v square by c square. This will be the limitations. Look, you need to maintain the frequency. Just a moment, let me just close the window. Now you need to maintain the frequency of revolution f is equals to bq by 2 pi m, right? Now if this m not remain fixed, so it becomes bq by 2 pi into mc square. If I write it bq c square, let's say we have to write 2 pi mc square. So this is equals to bq c square divided by 2 pi mc square is the total energy. So it is a sum of kinetic rest mass energy plus. So the resonance condition is disturbed. Okay. Therefore, for relativistic mass increase, the resonance condition will not be established. Okay. Electrons cannot be accelerated here. Yes. So you can see for using linac also and using cyclotron also, we are not able to accelerate electrons. For electrons we need Betatron, that we will discuss next. So using Betatron we will be able to accelerate electrons, light particles like electrons. Okay, now let's do some problem. Give it a try. An alpha particle is accelerated in a cyclotron. It leaves the cyclotron with a kinetic energy of 16 MeV. The potential difference between the d electrodes is 50 kilovolt. The number of revolutions the alpha particle makes in its spiral path before it leaves the cyclotron. I think you can do it. Do it quickly. This speed is 16 mega electron volt, its kinetic energy, and the potential between the electrodes 50 kilovolt. Number of revolutions n you have to find out. Can you not do it? I have already told you the formula. Wk for one gap qb, for two gap 2qb, n number of revolution n times 2qb. Okay. Alpha particle, what is the charge of the alpha particle? It is 2He4. So what is the charge of this alpha particle? It has 2 electrons, right? 2 electrons, 2 protons, 2 neutrons. So charge of an atom is decided by the charge of the electrons. So Q is equals to 2 times charge of the electron, 2 into 1.6 10 to the power minus 19 coulomb. So you can see n is equals to Wk by 2qv. D you are getting, very good, D will be the answer. So it is 16 mega electron volt 10 to the power 6 into 10.6 10 to the minus 19 divided by 2 times q. 2 times q is 2 into 2 into 1.6 10 to the power minus 19. Okay, and into V. V is 50 kilovolt. It will come out to be 80. Hello, next, do this problem. The value of the magnetic field required to maintain non-relativistic protons of energy 1 MeV in a circular orbit of radius 100 mm is how much Tesla? This was a very simple problem. Just do it. Kinetic energy is given 1 MeV. Half mv square is given to you. R is given to you. You have to find out B. R is equals to mv by bq. So B is equals to mv by qr. Give it a try, guys. Kinetic energy half mv square is equals to 1 mega electron volt. From this you can get the value of V square root of 1.6 10 to the power minus 13 divided by m. अच्छा 2 भी multiplied होगा, 2 into 1.6 divided by m. M is the mass of the what has been accelerated protons. Mass of proton, you know, 1.67 10 to the power minus 27 kilogram. Okay. So if you calculate this, you will get root over 1.91677 10 to the power 14, and that leads to 1.384 10 to the power 7 meter per second. So you get the velocity. Now to calculate the magnetic field, we can use R is equals to mv by bq. That means B is equals to mv by qr. So m we know, 1.67 10 to the power minus 27 kilogram. V we have calculated 1.384 10 to the power 7 upon Q charge of a proton is equal to the charge of an electron 1.6 10 to the minus 19 into radius is given 100 millimeter, 100 into 10 to the power minus 3. If you evaluate this, you will get around 1.4450 Tesla. It is matching with option A. Clear? Now, especially to accelerate electrons and to maintain the phase relationships, Betatron is used. Yes, Harry. Option A. Let's move on to Betatron. In Betatron, what is done? Instead of accelerating into different radius, it is accelerated at a constant radius. Now, Betatron consists of a highly evacuated angular tube D known as the donut chamber. You can see this is the donut chamber. The chamber is placed in between the poles of an electromagnet excited by an alternating current, frequency 60 or 180 Hz. Electrons are produced by electron gun and injected into the donut at the beginning of each cycle of the alternating current. The increasing magnetic field flux gives rise to a voltage gradient or electric field around the donut, which accelerates the orbiting electrons. Okay. So this is a cross section given to you, right? This is a cross section. It is like we have the north pole. Here we have the south pole. So you can see the magnetic field lines will be from north to south in this way, north to south. Here the field lines will be a little bit bent, and your particle is getting accelerated in this form. Okay, you can see it's coming in this way. So we're just showing you the cross section. In this magnetic field, the particle is getting accelerated. So it is accelerated at a constant radius. R value is fixed. Donut shaped means this. You see, okay, let me just draw it for you. These are specially designed pole pieces. So these are the magnetic poles. Okay? Magnetic poles. So we have the magnetic field lines existed in this way. So here it will be like this. This is the magnetic field lines. You can see the direction from north pole to south pole. Now here we have a donut shaped chamber. This is the donut shaped chamber. Okay. Donut shaped vacuum chamber. So you imagine it in 3D, okay? You imagine it in this way. You imagine it in this way. This is a donut shaped. Don't think that how it will go from here to here. It is in the 3D. Donut you have seen, na? Donut is the donut comes in the form of a circle like this. I have just shown you from side. You just extend it in this way. Have you eaten jalebi? Jalebi is like mostly donut shaped. Understood donut, Harry? The cyclotron cannot be used to accelerate electron. Yeah, that is what we are discussing. The cyclotron cannot be used to accelerate electron as their relativistic mass increase even at low energy is quite high. The above difficulty is overcome in the Betatron called the induction accelerator. What is the basic principle? What is followed in Betatron? Here the basic principle is to accelerate electrons in a stable orbit of essentially constant radius by the application of alternating magnetic field called the induction field. Induction field, the field we apply here, as you can see, between these two magnetic pole pieces, we apply some alternating magnetic field. So it does two effects. Firstly, the increasing magnetic flux produces an electromagnetic force, EMF it produces. So if you change the flux, so it will produce EMF, right? E equals to minus d phi by dt, we have seen. That accelerates the electrons along their orbits and thus increase their energy in each successive orbital revolution. Change in flux creates electromagnetic force and the particle get accelerated while maintaining the constant radius. So electron, it will speed up. Secondly, the varying magnetic field acting perpendicular to the electron orbit simultaneously constrains the electron move in a circular trajectory of constant radius. Okay, so the increasing magnetic flux, what is that? It speeds up the electron, and the varying magnetic field which is kept perpendicular to this electron's orbit, it keep it at the constant radius r. So two things, speed is constantly increasing and the radius is maintained constant. And as these two things operates in synchronization, we don't have the effect of relativistic mass increase. So the Betatron condition You see, the Betatron condition is d phi by dt is equals to 2 pi r square dB by dt. Phi is the magnetic flux enclosed by the orbiting electron. This is called the Betatron condition. It must be satisfied during the entire period of acceleration if the electrons are to be kept on the track of a constant radius. So if you integrate it, you get phi is equals to 2 pi square times. Look, phi is equals to 2 pi r square times b. For uniform magnetic induction, flux should be pi r square b. Thus, for a stable orbit of constant radius, the pole pieces of the magnet are to be so designed that the flux must change at the rate twice the rate at which it would have changed if the magnetic induction were uniform throughout the area enclosed by the orbit. Okay. Alternating magnetic field, you can say, imagine B, if you make it constant, it is B. If you vary with time, okay, na, it is dependent on time. So we are changing the magnetic field, means dB by dt is not 0. So this is the alternating magnetic field, not constant magnetic field. So this is done by electromagnetic EMF is generated. So it is done by the induction. By changing current, you can change the magnetic field. There is the relationship, I think, B is equals to mu naught Ni. So it is this B is directly related to current. Now if you change current, B will be changing, and if B changes, magnetic flux will change. Magnetic flux change means EMF will be created. Okay, and that EMF, electromagnetic force, will accelerate the electron and the particle will get speed up. Now to maintain it into a constant radius, this varying magnetic field is also perpendicular to the electron. It acts and does the job. Okay, so let's do some mathematics now. Energy calculation, we will calculate energy calculation. The calculation is a little bit odd. What is the momentum imparted to an electron of charge E by a field B is given by. So what is the formula of momentum? Momentum is equals to mass time velocity. Okay, now mb, you know, when a particle moves in a circular orbit, r is equals to mb by bq. So mb is equals to bqr. So b e r, because q is equals to e. Clear? Therefore the energy will become relativistic. Okay, na? It is an electron. So if we consider relativistic energy, no, E is equals to h cut square k square by 2m, or p square by 2m you generally use for non-relativistic particle. But for relativistic particle like photons, we use E is equals to pc. This expression is used, right? So once when you are accelerating the electrons, it is going into relativistic speed. It is achieving the relativistic speed. So its energy will be written as E is equals to Pc in this form. So B is equals to BER, BRC. You can remember this. Bhabha Atomic Research Center type, but A is E here, BERC. The energy is BRC. So what is this B? B is not constant, it is constantly increasing, right? So where this B is the magnetic field at the end of the accelerating time. When the acceleration process is end, at that time whatever is the B value, that is the B value we need to use here. What is the accelerating time? In Betatron, the accelerating time is T by 4. So for linac it is T by 2. For cyclotron it is, okay, for cyclotron what it was? T by 2, and here it is T by 4. Sorry, T by 2, T by 4. So you see, T by 4, 1 by 4, T is equals to 2 pi by omega. So this is pi by 2 omega. Now how much distance the electron travels in this time? Distance traveled by the electron in time T by 4 is, we can say D is equals to, distance is equals to velocity into time. So time is T by 4, so pi by 2 omega into speed if I take the speed of light, it is pi c by 2 omega. So this is an approximate expression. We can take it this much of distance it travels. So can you calculate the number of revolutions? Number of revolutions executed per second. By the electron. Of course we can. So what is the number of revolution? You see, it has traveled in one cycle. You see, the accelerating time is T by 4. In T by 4 it has traveled a distance D, right? But the path of the electron, as you can see, the path of the electron is circular, right? So if I want to calculate the number of revolutions, if you know the total distance travels, how can you calculate the number of revolutions? If we divide the total distance traveled divided by the perimeter of this, okay, in one revolution how much distance it is covering? It is 2 pi r. So if I had covered a total distance of d, the number of revolutions will be d by 2 pi r. Simple. Now d we have got pi c divided by 2 omega into 1 by 2 pi. This pi getting cancelled, so it is c by 4 omega. You know all the values. C is the speed of light, omega is the angular frequency, r is the radius. R is the radius of the stable orbit. Here we have only one radius, so we don't have problem. So as you are increasing the magnetic field, the flux changes, and each time the flux changes, electromagnetic force is acting on the electron and it increases the energy of the electron, right? Now can we calculate per second how much energy the electron is gaining? Can you calculate how much energy the electron is gaining when the flux changes with time? The energy gained by the electron per second each. Obviously, to change the magnetic field, to make the magnetic field alternating magnetic field, we need to give you need to vary it sinusoidally, right? So what is the energy gained by the electron? We can write E times d phi by dt. Okay, so E is the charge time voltage. So d phi by dt is equals to voltage, okay na, electromotive. E times d phi by dt. D phi by dt is like voltage. The way you use the formula of Q into V, so it is like the V. So E times d dt of phi. Phi, as you know, the magnetic flux should be varying sinusoidally to get alternating magnetic field. So phi naught sine omega t. So this is E omega phi naught cos omega t. Can you write it? This is the energy gained by the electron per second. So in 1 second, this much of energy it is gaining. So can you calculate, like in one cycle or in each revolution, how much energy is gained? Therefore, the energy gained in each revolution, so for one revolution, how much time is required? T by 4, right? This is accelerating time, T by 4. So 0 to T by 4. In 1 second, it is E omega phi naught cos omega t dt divided by 0 to T by 4 dt. Can you write it? So this will come out to be twice E omega phi naught divided by pi. So this is the energy gained in one revolution. So what is the total energy gained in n revolutions? Therefore, the total energy gained or imparted to the electron in n revolutions is how much? You can say ET. This is the mean energy per revolution multiplied by number of revolutions. So what is the mean energy per revolution? We have got it, this 2 E omega phi naught divided by pi. This is the energy imparted on the electron in one revolution. So in n number of revolution, what you have, n is number of revolution n is equals to how much? We have calculated c by 4 omega r. So put the value c by 4 omega r. If we calculate this, how much you get? EC phi naught, omega is getting cancelled, 2 cancel with 2, so EC phi naught by 2 pi r. This is the total energy imparted to the electron in n revolutions. Clear? So this is all about this Betatron. Now what is this use? Obviously the use is to accelerate electrons. Usefulness, so it can accelerate energies to accelerate it can accelerate and it can energize electrons up to 100 mega electron volt. In this case, mass of the electron, yeah, that thing is controlled by the combined effect of this alternating magnetic field. Now here also it imposes the restriction. Look, previously it was accelerated into different radius, so that is why relativistic mass increase was the problem to maintain the synchronization. Here, although it can accelerate to a higher energy, but it also had some limitations. Limitation is from the relativistic mass increase only, but it is not so much pronounced here because of the combined effect, but still it has the limitation of the orbital stability. Maintaining a constant radius is a challenge here. Okay, so here the limitation is the problem of orbital stability. So this is the limitation. So if you increase the energy too much, then orbital stability will be hampered, but it can relatively energize the electron up to a higher energy, which is not possible in the case of cyclotron. Okay, is it clear, guys? Let me just give you the summary, then we'll end the session here. Here we'll be writing the accelerators, accelerating particles, and energize up to. Accelerators, particles to be accelerated, energized up to. Firstly, the linear accelerators. This is also called linacs. Linacs, you can accelerate protons or heavier ions. You can accelerate up to 32 MeV. Second type, you can take cyclotron. Cyclotron can accelerate protons, deuterons, alpha particles. It can accelerate up to 10 to 50 MeV. In this range, it works well. Third is Betatron. Betatron can energize electrons. It can energize up to 100 MeV. Up to 100 MeV, there will be no problem of orbital stability. But beyond this range, you will get the problem of orbital stability. Means it will not be possible to maintain the electron into a constant radius by the arrangement you made in this Betatron. So I hope this single lecture is enough for these particle accelerators. These are the accelerators you will get, and you get very easy questions. If you know about these equations and all, you can easily solve questions. We have already solved few problems, and this particular topic is especially important for GATE exam. In NET exam, generally they don't ask. They ask from the detector part, which we'll be doing in the next class. Okay, on the next class we'll be discussing the detectors. Accelerator is done, we'll go for detector, and after that our nuclear physics will be over. So one more lecture and we will be completing nuclear physics. This is what is the lecture number today. This is lecture number 18. So in lecture number 19, our whole nuclear physics will be completed, and maybe another lecture we can set up. So 20 almost. So we are stopping here today, guys. Thank you very much. If you have any question, you can let me know. Otherwise, we'll stop the session. Have a great day, guys.